Hello, and welcome to Photonics Next. In our next session, Photonics Test and Control Solutions for Quantum Applications. I'm Justine Murphy, Senior Editor of Laser Focus World. If you experience any technical difficulties during this session, just type your issue into the Ask a Question window on the side of your screen, and our technical experts will be happy to assist you. We recommend disabling any pop-up blocking software or extensions in your browser because sometimes these cause issues with the webinar player. We welcome your questions during this session, and you can send them at any time by simply typing into that same Ask a Question box and hitting Submit. Our speaker will reach out separately later after the presentation is over to answer all questions. And please be aware that this session is being recorded, and you'll be notified by email when the archive is available. And now let's meet our speaker, Wajid Daab, Director of Business Development at Luna Innovations. He has over 10 years of experience in managing, selling, and marketing high-technology photonics products. Hello, Wajid. We're so happy to have you here.
Thank you, Justin. Thank you.
And the floor is yours.
Okay. Thank you, everyone. I appreciate the time joining this talk about Luna solutions for quantum applications. Before I start talking about our solutions, I would like just to give a brief introduction to the Luna Innovations. Luna is a global company where the headquarters is in Roanoke, Virginia, and we have multiple manufacturing and sales sites in the US and in Europe. We are roughly 350 people. The business is divided into main areas: communication test or photonics test, as well as sensing. We have a lot of patents about photonics technologies, and we have multiple locations, roughly 12 in Europe and the US. The business, as I mentioned, we have a lot of solutions for sensing that can measure and monitor any assets, but the focus for this talk is going to be around our comms test products, where we have a lot of products that can measure, control light with focus on quantum related applications. So Luna has a lot of products, and we are vertically integrated. We have so many OEM photonics that are sold to all of our customers, but also are being used in our test and measurement solutions and our sensing solutions. So I will be focusing more on our OEM solutions for quantum applications, but also I will spend a few slides talking about our test and measurement solutions for quantum integrated photonics. Next, talking about the quantum revolutions. As some of you is aware, the quantum revolution one took place in the early 1900s, where it gave us information about the physical reality. We understood how maybe electrons behave or photons behave, but the technology and the experimental capabilities were not ready to really test the fundamentals of quantum mechanics. So now we are actually in the quantum revolution 2, where we are using the principles of quantum mechanics to control, manipulate, and generate man-made quantum states, which will have applications in a variety of industries, with bringing a lot of advantages over the classical way of making any optical measurements, for example. And because of the recent advances in controlling, as I mentioned, the photons and the atoms and electrons, this enabled advances in 3 main areas. And these are the 3 main areas that Luna is focusing on. And we try to support the engineering and research effort in these 3 main areas. The first area is in the quantum computing, and this is to have a quantum computer that's much powerful in terms of the computational speeds than the current semiconductor-based computers. The second area is quantum communications and quantum information technology, where we have an ultra-secure communication links. And the third is quantum sensing or metrology, where we are building quantum-based sensing measurement systems, which have extreme sensitivity, much higher than what's available with classical physics. So I'm gonna briefly talk about these 3 main areas and what are the photonics related functions that might be needed and then I will present our solutions for these quantum challenges when it comes to controlling and manipulating light. So for quantum communications, there are multiple techniques. The ultimate goal is to have a secure link. So in this example, we have two parties where they can exchange encrypted data on the regular telecom channel, but then they share the keys to decrypt this data using the quantum states. So any interruption, any trial to read such quantum state is going to fail, and then we can tell and we can exchange the key. So it is one of the protocols that's being used. Obviously, there are the most common one is the quantum key distribution. There are multiple methods and protocols under the quantum key distribution umbrella. One of them is the polarization encoding QKD. In this work, and you can see the reference on the slide, they achieved a communication link based on quantum principles over 50 kilometers. And this setup, they needed polarization controllers and they needed laser or light sources. The other example is a twin field QKD, where the team achieved over 300 quantum communication link over 300 kilometers without a need for repeaters. In this setup, they needed 3 lasers, so 1 master, 2 slaves. They are synchronized together. They need polarization controllers. They need phase shifters to build such system. So in the communication, the quantum communication area, obviously there's a need for a good narrow line width source. There's a need for polarization controllers and phase controllers. Moving to the second area is the quantum sensing, and the most successful example is the quantum gravimeters, which are needed in geoscience to understand the subsurface mass distribution as an example. But in this example, there is a need for narrow line width laser at 780. And there's a need for polarization controllers. One of the techniques that can be used, because Luna doesn't have narrow line width laser at 1550, is to build the second harmonic generation setup where a 1560 nanometer laser is being amplified. Its polarization is controlled and then passed through a PPLN crystal that will double the frequency, and we will end up with 780 nanometer, which is ideal for rubidium atom transitions. So that's how our solutions been used in quantum sensing. And finally, quantum computing, and this is an example of an important building block, which is a degenerate squeezed light generation on a chip, on a photonics integrated circuit. And this work done, there's a need for narrow line width lasers that will be synchronized together. There's a need for polarization controllers, phase shifters, and could be a need for filters. So now, after understanding some of the functions that are needed in those 3 areas, I would like to talk about what Luna has to offer to these applications. Before going to that, I just want to briefly mention that for quantum computing, there are multiple hardwares. There's the superconducting, trapped ions, cold atoms, but Luna has more products to offer to the photonics-based quantum computing because of our photonics solutions. In addition, some of these photonics-based quantum computers, they have a quantum photonics integrated circuits. These quantum integrated circuits may have a single photon source, or may have a quantum frequency comb, or the design is meant for an ultra low loss design. We have the test and measurement capabilities to characterize photonics integrated circuit and look inside them with very high spatial resolution. So I will mention our technology that's suitable for characterizing integrated photonics. I also want to mention that even though the whole focus is on photonics-based quantum computing, Luna still offers narrow linewidth lasers for ion trapping and neutral atoms and atom clone related applications. So that's also still an attractive solution to customers in these areas. So going now to our solutions. So Luna has a lot of test and measurement solutions, polarization controllers for polarization measurements, and OBR-based reflectometers. And then we have multiple OEM photonics modules. They are centered around multiple functions, polarization, multiple photonics functions. So we have polarization controlling modules that are fiber-based. We have delay phase modules. It can control the phase and the delay, so different delay ranges. We have narrow linewidth laser that's semiconductor-based, and we have fabricator or tunable filters, and we have coils. And coils in quantum applications normally are they are being used as a quantum memory. So we have different designs, and we can control and keeping the loss very low. In addition to the separate components, we do offer a higher levels integration services. So for certain applications where there's a need for combining some of these components, we have the ability to integrate those and put them in a one package for specific applications. The example would be in interferometric based quantum systems. Sometimes there's a need for interfering single photons, and for any interferometric setup, there's a need for controlling the phase, polarization, and fast phase drifting. So we can put those components together in a subassembly to achieve four main functions. Control and track the polarization. So we know polarization always drifts, so we can track and control it. Fast phase detuning and slow phase adjustments, and then quantum memory, which is again used as a delay coil. So we delay the photons by a certain amount of delay, and use that to before we manipulate the quantum photon after that. Now going to our test and measurement solutions, I want to mention that we have a lot of polarization related instruments. So I'm not gonna focus on this. I'm gonna focus on our OBR based test and measurement solutions. These OBRs, they are based on OFDR technology. So we sweep the wavelengths and we send the light to the sample. We receive it, we interfere it with a reference light, and we extract information about the reflections and the locations versus time or versus wavelength. So we have multiple solutions that use this technology. You can see here is a comparison of all the measurements that can be captured or taken with some of these instruments. So we can measure distributed insertion loss, distributed return loss, reflectivity, frequency, wavelength analysis, backscatter, attenuation in the waveguide, in addition to polarization and dispersion information. This is a good example of scanning a semiconductor-based external cavity laser. So it has a gain chip PLC with the printed FPGs. They form external cavity setup, and we use our OBR 4600 to characterize this laser. So we have two data. We have time domain analysis data and frequency domain analysis data. For the time domain, you can see we have multiple information about the laser. We can locate the lenses, the beginning of the fiber Bragg rating planar waveguide. We can locate the gain chip. We can scan inside or outside the Bragg wavelength to gather more information. You can see the ring down, which will tell you the cavity loss. So a lot of details about what's happening inside the laser. At the same time, for the frequency domain, once you zoom on one of the features, you can get the frequency response, or here we can see the center frequency. It's around 1555 roughly nanometer, and you can see the group delay inside the passband. So you can see there's a slope. All of this information are useful to improve the design of the laser. Talking about our polarization technologies, briefly, we have multiple technologies: fiber-based, lithium niobate-based, and magneto-optic crystal-based. And we have multiple solutions under each. In quantum, it's more attractive to go with the fiber-based squeezing technology because of the lossless design. It is less than 0.05 dB, which is very attractive in quantum applications. So we have a lot of polarization controlling and tracking products under that category. This is just a performance data. You can see here our tracking. We can track a sudden change in polarization in less than half millisecond. This graph shows the total switching time of less than 50 microsecond. The response time is actually 10 microsecond, but the total switching time for polarization switch is less than 50 microsecond. For the hour phase and delay, we have two technologies. We have the fiber-based, and also this is attractive because it's low loss, and we can achieve phase delay from a few pi's to 15, 55, 75 pi's, all the way to 3 millimeter in air, depending on the length and the design. But here we can, in the kilohertz region, we can modulate the phase to do the phase detuning. For other applications where higher insertion loss can be tolerated, we have free space fiber coupled design, which can delay the photon or the signal up to 1.1 nanosecond delay. And these are the insertion loss ranges in the 1 to 2 dB. So this is very attractive in some quantum computing related applications. This is an example of the performance data. You can see here the linear relationship between applying voltage and the achieved phase shift. Or you can see in this example, we can reach up to 80 pi phase shift. For MDL, you can see the insertion loss over the delay range. It's relatively stable, and it's around between 1 all the way to less than 1.5 dB, depending on the model. And this showing for FPS 003, showing the resonance frequency around 37 kilohertz. But you can see that we can achieve up to 51 pi phase shift. For the coiling, we have a lot of winding capabilities and options. We can design coils and quantum memories with very accurate length and delay, because we have the OBR capability to really control the length of the coil and keeping the loss very low. So we have a lot of options there. For our nanoline with laser, as I mentioned, our Rio laser is based on a semiconductor design, and we can achieve 10 to 20 milliwatt. Sometimes we do 30 milliwatt in a special solution, but our product is offered at 1 micron region and at 1550 Windows C-band. Any wavelengths in the C-band can be done. We have the Planix, which is the 14-pin butterfly, but also we have the Orion, which comes with a driver board, and we have the Grandi, which comes with an amplifier to achieve higher output powers up to 2 watts. But what's good about this design is the reliability, the very compact ultra nanoline with less than 1 kilohertz can be achieved, very low noise, very attractive in quantum applications. I just want to briefly mention some of the features for Rio laser. Its stability. We have very good stability, and we are comparing the results versus other fiber-based lasers. We can achieve very high stability over a short period of time. There is no need for warming, few seconds, and it can stabilize the output wavelengths. The other feature is the ability to do frequency and FM and AM modulation. So with a direct current, you can modulate the frequency of the output of the laser. Also, we have different grades. We have less than 1 kilohertz, less than 2, less than 5, less than 15. This is really to target more applications and achieve and meeting the customer requirements with the lowest cost. So for certain application where it's very demanding and requires the highest performance, then we go for grade 5, which can achieve less than 1 kilohertz line width. And going to our Fabry-Pero based tunable filters, these are all fiber-based, ideal for OEM applications, they're qualified, very low insertion loss, very customizable. So we have different wavelengths we can offer all the way to 2000 nanometers. We work with our customers to specify the spectral range and the finesse, and from that we come up with a design. We have multiple configurations. We have the tunable filter, we have the interferometer, we have the scanning interferometer, and we have the athermal filter. So depending on the application, depending on the requirements, we have hopefully we have the right solution. When it comes to the wavelengths that we offer at Luna for different applications, this is our understanding of the major wavelengths that are needed for each area. For quantum computing, 1550 to 1510, and now we are seeing 1 micron. For quantum communications, we see more 1550. For quantum sensing, from 780 all the way to 1550, so it's broad. At Luna, we have OBR instruments standard for 1550 and 1310 nanometer, but also coming soon, we're going to offer OBR at 1 micron. Our polarization instruments offered as a standard from 1 micron all the way to 1550 nanometer window. Our polarization modules can be offered from 700 all the way to 1550, even 2 micron, because it's fiber-based and we can replace the fiber. And that's true for our fiber phase shifters and coils. Our Rio laser, as I mentioned, it's only offered at 1550 and 1 micron, and our tunable filters can cover all the wavelengths of interest, so we don't have any issues. So here is a summary. Luna has expertise in polarization, delay, and fiber coil products. It's very attractive in quantum-related applications. We are happy to custom and tailor our solutions if our standard solutions cannot fulfill the requirements. We are considering any customization. We have strong test and measurement capabilities to qualify and characterize components on the component level and in the sub-integrated level. Our OBR technology is ideal for component characterization, coil characterization, interferometers characterization, and even waveguides characterization. And we have comprehensive testing and manufacturing capabilities. So we are pursuing multiple OEMs in each of these areas already. So we are happy to learn more about your challenges and see how Luna can help. And that's the end of my presentation. If you have any questions, feel free to reach me by email or phone. Thank you so much.
Wonderful. Thank you. Anything quantum related really is just so fascinating. That was great. And we are just about out of time. So on behalf of Laser Focus World, I'd like to thank Wajid Dab for such a great presentation. And of course, all of you too for joining us. And once we're done here, a quick survey will pop up. We encourage you to share your thoughts with us. It helps guide our planning of future Photonics Next content. And don't miss our final keynote session of this year's event, measuring single photons with superconducting nanowire detectors. You can join that by exiting out of this event and going back into the agenda. Thank you again to Wajid Dab and all of you for attending the session.
Thank you.